Good day, grade 10s. Today we are talking about multiplying polynomials, whereas last day we were multiplying polynomials. But the difference is, today we are going to multiply polynomials without algebra tiles. We'll start off though with a little bit of a transition and a reminder of how we could multiply a binomial times a binomial with algebra tiles. So the first thing to do is represent the length times the width as our length x plus 2 and our length x plus a 3, and we do this with the idea that this is a length, this is a width, and what gets created is some sort of area. That's a multiplication can be considered. Well, we have the length of x, we have a length of x, and together that length of x and length of x multiply together to create an x squared. We have a length of 1 and a length of x which come together to make another x, a length of x, a length of 1, that will make another x. So these are both x's. For the bottom we've got a length of x which times is by a length of 1, so a length of x, length of 1, and this creates an x, another x, and another x. Be clear in where these are being written and the horizontal effect of those ones and the vertical effect of those on the right. Now we do have a 1 times a 1 that makes a 1, a 1 times a 1 that makes a 1, and this happens a few times. Okay, 1 times 1, 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 1 times 1. Ultimately, when we're combining all the like terms, what we have for a product of x plus 2 times x plus 3 is 1x squared. There are 5 x's, and there is 1, 2, 3, 4, 5, 6 ones. So this is the area, or this is the product, this is the result of multiplying together a binomial times a binomial using algebra tiles. Now you actually learned in a previous grade how to deal with a monomial times a binomial without algebra tiles. And eventually you got to the place where you could say, all right, we're saying 2 times x, and we are saying 2 times 3. Each of those is and can be considered a bit of a product. Pretend for a moment, again going back to this example, pretend for a moment you had a basket with 3 apples and 4 bananas, and if you had 3 of these, it really is considering this as a bracket, and there's a 3a and a 4b, which is being multiplied by a 3. If you had 3 of these brackets or baskets, you'd have 9 apples and 12 bananas. Same effect out of context means we've got 2 x's and 2 3's. 2 3's is 3 plus 3, which is 6. So we were able to do this in previous years without actually drawing algebra tiles, and that's maybe the type of logic that we want to eventually get to. So in example 1 at the very, very bottom, what we've got is same question, how can we approach this without algebra tiles? So it's important to know that there is a transition from one approach to the other. If I were to say x plus 2, I'm going to now represent this without drawing a tile, and I'm just going to say it has a value of x, and then I'm going to say plus 2. So I'm not drawing 2 singles, I'm saying x plus 2. And here I'm going to say x and a plus 3. Now what is occurring here is 4 products. There's going to be an x times an x, which goes there. We saw that above as our x squared. There's going to be an x times a 2, which makes a 2x, which is that 2x. We're going to have an x times a 3, which is our 3x's. And we're going to have a 2 times a 3, which is going to make the 6. Instead of drawing them out, we can simply say it's an x squared, x times 2, 2x, x times 3, 3x, 3 times 2, 6. Combining all the like terms, it's actually more of an algebraic understanding now, and we can say that certain things are connecting. What I'd like to do before we just add those up is actually start to connect the dots between something even simpler than that. If I were to say the x and the x connect, I'm going to now draw an arrow going from the x to the x and say that should be a product. We're also connecting an x times a 2, an x times a 3, and a 3 times a 2. Every one of these is going to be arrows. Let's just next go and say an x times a 3 is going to connect to make a 3x. So I'm going to say there's going to be an x times a 3 that connects. There's going to be an x times a 2. There's going to be a 3 times a 2, which makes a 6. So essentially, 4 arrows occurred. The first number in the binomial connected to both in the second. The second number in your binomial connected to both in the second. And if you could actually draw 4 arrows that connect to the right locations, what you end up with is your answer. An x squared plus a 3x plus a 2x plus a 6x, and ultimately x squared plus 5x plus 6. This is going to be the choice and the approach that we're going to employ, where each term in the polynomial needs to connect with each term in the other polynomial. This is called the distributive property, and this is what we're going to apply. So if that is making some sense, let's flip it on over and try another example, maybe without algebra tiles. So 4 arrows need to be drawn to connect these 4 terms. So we have a 2x times an x. The 2x has to connect now to the other one, the negative 3. And now the 5, this has to connect to both. Has to connect to the x, has to connect to the negative 3. You just have to be very, very, very careful. The first arrow was 2x times x. 2x times x makes 2x squared. If you really, really, really wanted, you're more than welcome to write out each arrow. So this was a result of 2x times x. Your next arrow is 2x times negative 3. 2x times negative 3. That's a negative 6 and 1x. Your third arrow is the 5 times the x, which makes positive 5x. And lastly, the 5 times the negative 3 is the last combination here, and a 5 times a negative 3 is a negative 15. And when you combine all the like terms, which essentially is only the middle two, a negative 6 plus a 5 makes a negative 1x. So 2x squared minus 1x or minus x. Minus 15 is the answer. You are going to get much better at this, where you might not need to draw out each product, and you can do each question, each arrow, sort of in your head. Now, we'll step this up a notch, and you're going to have more to practice like this, but we're going to try some which are ramped up in difficulty because you're already saying, too easy, I got this. Well, in example 3, we've got a binomial times 3 terms. That's a trinomial, a monomial times a trinomial. Well, the 2h has to connect to the h squared, the 3h, and the negative 4. Well, that means we've got 3 arrows, 3 products. We'll do the bottom 3 after, but we've got a 2h times h, 2h cubed. Okay, this is an h to the 1, this is an h to the 2. We add the powers to make an h cubed. H to the 1, h to the 2 makes an h cubed. Your second arrow is 2h times 3h. 2h times 3h makes a 6h squared. And these are the ones that we've struggled with in the past. When we've got an h times an h makes an h squared, and the 2 times the 3 makes the 6. All right, so the last arrow is a 2h times a negative 4, a negative 4h. Now we've got 3 more arrows, and I'll do these ones in pencil as a different color. 1, 2, 3. The 5 had to connect to all 3 terms, which creates 3 more products. So we have a positive 5h squared for the first arrow. We have a 5h times a 3h makes a 15h. And the very, very last one, a 5 times a negative 4 makes a negative 20. And these are the 1, 2, 3, 4, 5, 6 different arrows products that resulted. Now we get to combine any like terms. And as we examine what's left over, I see an h cubed. I don't see any more h cubes, so there's no other like terms like it. So the final answer is going to involve a 2h cubed. And I'll just maybe cross it off to make sure we know that we've dealt with it. Do you see any h squareds? And I do see one there and one there. So let's combine those together for our next one. There's a 6h squared and a 5h squared makes an 11h squared. When we're adding like terms, only the coefficients change. So we'll cross those off to say they've been dealt with. And then the h to the ones, the h's. There's a -8 and a +15. It's -8 degrees, and you go up 15 degrees means we are at 7h. Dealt with those, and now we have a subtracting a 20. This is the product of a monomial times a binomial. A bit more work, but perhaps as tricky and expanding as you might get. So with that in mind, it might be worth, if you wanted to pause a video. If not, just keep going, and you can try these as we go. So, monomial times a binomial times a trinomial, 2 terms, 3 terms, 3 arrows for the top, 3 arrows for the bottom. And again, it's worth giving this a try, but I will just keep talking and rambling. We have a 3k cubed minus a 3k, negative 2k, negative 6k squared. Last arrow is a 3k times a -7, negative 21k. For the bottom 3, we've got a 4 times a k squared, 4k squared. 4 times a negative 2k, negative 8k. And the last one is a negative 28. Combining our like terms, there is a 3k cubed. There's 2k squared terms. Combining them results in a negative 2k squared. These combine both negative to a negative 29k, and a negative 28 is left over. And the very bottom question is intended just to remind us that sometimes questions can feel a little bit misleading. This one is saying 2k plus 3 squared. It's important to remember what squaring means, and as an aside, if I were to ask you to evaluate 3 squared, you might say 3, not 3 times 2, but 3 times itself. That's what squaring something is. Let's approach this logic by timesing the base by itself. So when we're told that 2k plus 3 is squared, we're being told that it's 2k plus 3 times itself, which means there is 4 arrows. 4k squared for the first arrow, 6k for the second, 6k for the third, and the last one, the 3 times a 3 makes a 9, and a final answer, when piecing it all together, is a 4k squared plus 12k plus 9. Final answer. So be careful if you ever see something that is being squared, it actually means times itself. Well, we've only got a couple more questions to employ. There is a 6, 7, and a bit of an extension at the bottom. And example 6 is a little bit of an interesting case because there's a 2k minus 3 and a 2k plus 3. Perhaps not squaring the same binomial because one's a negative and one's a positive. And something interesting happens in this example. So again, if you wanted to pause it and then retry it, you're more than welcome to. 2k times 2k makes a 4k squared. 2k times 3 makes a 6k. A negative 3 times a 2k makes a negative 6k. Interesting with those k to the ones. And the last arrow is a 3 and a negative 3 makes a negative 9. Well, conveniently, the middle terms are kind of opposites of each other. One's positive 6, one's negative 6, and they cancel each other out. A final answer is a 4k squared, subtract a 9. As you do more practice, you start to learn that there are strategies and special cases that do result, but this only does come with more practice. Example 7 is a little bit crazier because you've got a trinomial times a trinomial. If you're feeling a little bit nervous, you might not attempt this one yet, but if you're feeling like this has made sense, it's worth giving it a try. So we're going to continue this one, and if you want to again pause the video, otherwise continue. So in this one, you've got a 2x squared. That's going to have to connect to everything in the trinomial on the right. Remember, what we're doing with the distributive property is saying that each term in the polynomial needs to connect with each term in the other polynomial. That's what we're doing. The 2x squared needs to connect to everything in the second one. And this is 3 arrows. I'm going to save a little bit of space because we might run out of room. First arrow, 2x to the 4. Second arrow, 4x cubed. Last arrow is an 8x squared. Now what's strange is we actually have 2 more terms left. So I'm going to stick with the top side here and take this negative x and do 3 more arrows. So that negative x has to connect with everything in the second term. So we continue with a negative x times an x squared, a negative x times a 2x, and the last one a negative x times a 4. Now we are actually left with the positive 3, which connects with the 3 terms again. I know. So we have a 3 times an x squared, a 3 times a 2x, and a 3 times a 4. Combining all like terms, you do have to be very careful examining all the x cubeds, all the x squareds, and there's actually 3 of those, all the x's, because there might be more than usual. So in combining all like terms, there's only the single 2x to the 4 term. The x cubeds, there's only 2 of them, a 4x cubed and a negative 1x cubed. Those will combine to a 3x cubed, 4 minus 1. In the x squareds, there's an 8x squared, subtract a 2x squared, plus a 3x squared. 8 minus 2 is 6, 6 plus 3 is 9 x squareds. And then for the x to the 1s, we're left with a negative 4x plus 6x, means we're left with a 2x, and then plus 12 at the very, very end. We'll box it up, final answer, but this is quite an intensive question. And the very last one is a little bit of an extension, which is very much still a part of our course. It's asking to determine the area of the shaded region. So the shaded region is sort of an area, but there's a little piece missing. If you think about this giant rectangle, it has lengths and widths that are algebraic. Let's call this maybe a large area, and the inside part is a smaller area. So if we look at the area that is subscript shaded, what we're trying to do is calculate the area of the larger rectangle and then subtract the area of the smaller, which is unshaded rectangle. Giant area, take away the area on the inside, and what's left over is the shaded region. So in representing the area of the larger region, we are taking your length and your width and multiplying them together. A 2x minus 2 times an x plus a 1, this is the area of the larger region, which we could eventually expand or multiply. Area of the smaller region is the unshaded x times x minus 2. Now we've actually done questions like this in the past where we can't do any subtraction because we've got some multiplying that happens first. So BADMAS forces us to multiply our binomials. So 2x times x, 2x squared. 2x times 1, 2x. Negative 2x, negative 2. And this is a result of your first area, which when we summarize it is a 2x squared. Ooh, these actually do cancel out very, very nicely because they are the same. Subtracted 2. We do have a negative x, which is going into the bracket, which means it's multiplying by it. Now this is not saying it's 2 or 3 baskets of apples and bananas. This is very much out of context, a number getting distributed into a bracket. It still is a negative x times an x, which is a negative x squared. It's a negative x times a negative 2, which makes a positive 2x. So this part gets dropped down, a negative x squared plus a 2x. Tidying this up gives us a 2x squared minus an x squared is an x squared. Positive 2x is the next term in descending order. And then lastly, there's a negative 2. And this is the variable or algebraic area of the shaded region. Thus, ending our lesson in multiplying without algebra tiles. Good luck.